Hello and welcome to this module. In this module, we'll talk about gamma ray imaging. In the previous module, we talked about how the detector records this 3D position of interaction for each gamma ray that comes and interacts with the detector, and also records the energy associated with each interaction. In this module, we'll see how we convert that information to some directionality or where the gamma ray could have possibly come from. This is our gamma ray detector. Inside there are 9 pixelated CZT detectors. This is the CZT detector. It's 2 by 2 by 1.5 centimeters, so it's about 6 centimeters cubed. It's about yay big. And on the anode side, there is an 11 by 11 pixelated array. Sorry, let me turn on the pen. There is an, not the pen, the laser. There's an 11 by 11 anode electrodes on the anode side, and then a planar cathode on the other side. And this is the geometry of the detector. It's attached to an ASIC, so an application-specific integrated circuit, and that records whatever triggered pixel it is, and it negotiates between all the 121 pixels. This is a cartoon of the detector, and you can see that the red is the pixels on the anode side, and then there's a planar cathode. The gamma ray comes in and interacts via quantum scattering, pair production, or photoelectric effect, and produces somehow an electron. That electron then drifts towards the anode. Now there's 3000 volts, that's why it drifts towards the anode. And because in CZT, the Hall movement, so the Hall is the vacancy from where the electron has left, the Hall movement is not very mobile. That is different than what you would have learned from a germanium detector. The electron drifts to the anode as such, and induces a charge that's independent of the depth of interaction. This is due to the weighting potential or the electric field of the electrodes on the anode side. The cathode side, however, is a planar cathode, is a planar geometry, and that produces a depth-dependent signal. This is a linear depth-dependent signal. So you have two signals, a depth-dependent signal, which is in the blue, that's from the cathode, and a depth-independent signal from the anode, which is in the red. You can take the ratios of the two, and that gives you information about the depth of interaction. This is the depth of interaction on this axis, and on this axis, it's the energy deposited or the amplitude of the signal. This is the photocathode, and you can see that there's a turning of the photocathode right here when the anode, when the depths are at very small distances away from the anode. That is because of the weighting potential effect of the detector. But we can fix this and apply gain correction for each depth. And this results in a very high energy spectrum. The way we convert this into the possible directions of where the gamma could have come from is in a process called Compton scattering. This is for gamma rays above 250 keV. Again, we know the X, Y, Z, and energy that associated with each interaction. So when a gamma ray comes in, it scatters off this location and then photoelectric effects at the second location. The way we estimate where the gamma ray could have come from is we draw a vector from the second to the first interaction like that. And we know the Compton scattering equation, which is shown right here. And we know that the energy deposited is a function of the scatter angle. So if we know the energy deposited, which we know from our detector, we can calculate the scatter angle of where the gamma ray, the possible scatter angle that the gamma ray could have come from. This is there right here. So all the possible locations or the locus of points revolve around this vector, which we call the lever arm. This produces a cone. So you imagine a cone coming out of this point right here. And this is another illustration of how this works. So this is the cone projected out from the interaction site. We back project this onto some image space, right? So you imagine that the detector, is in the middle of this sphere or this image space. And the cone, if you look from the center, is actually a ring. This is the ring right here. The ring is all the possible locations of where the gamma ray could have come from, right? It's not where the gamma ray came from, but could have come from. The true location where the gamma curve came from is this point right here. But because of the physics effect of the detector, we just have a guess of the locus of points where the gamma ray could have come from. So this is one projection. Let's add another event. So there's another interaction. And you can see that there's an overlap. Let's add some more interactions, and you can see that we're starting to form a hotspot. This is where the rings overlap most, and the most intense region is the most probable region of where the gamma ray could have come from. Again, the way you view this is that this is the sphere, and you're in the center of it, and the hotspot is coming from here. Let's add some more event, and you can see that we're converging onto a hotspot. This is the most probable location of where this could have come from. The way we image this is something called simple back projection. There is more advanced image reconstruction techniques like filtering, but we will not go into this technique in this module. So before we talked about Compton scattering, if we go to lower energies where the predominant gamma matter interaction is photoelectric effect, you cannot rely on scatter to do the imaging technique as I showed before. The way you do this is via a coded aperture or a pinhole camera. Just like a regular camera, which has some aperture and maybe a lens in front and then a CCD chip or some kind of silicon device in the back. This is the regular camera that is in the iPhone and this camera in front of me. This uses a very similar principle. Like a pinhole, right? There is a projection through that pinhole onto the image space. This is, we just poke more holes in the aperture to allow more light to go through. This increases the signal to noise ratio, right? So we don't have to, in the pinhole, right, there is very little light that comes in. In a coded aperture, there's more light. So imagine the source right here. This is the mask, the coded mask. So imagine this coded mask made out of something that's attenuating, right? The gamma can go through the holes, but it will be attenuated by the coded mask in front. The projection is projected then onto the detector, which is recording whatever projection is on the detector. So yeah, this is a flashlight, you're projecting the light, and this is some shadow that you're recording. This is the measurement, and the mask is in front of it. This is what you would measure. Now, what we do is we deconvolve what the mask is doing, or the aperture, and we can reconstruct the image source. The source distribution of whatever source you're trying to measure. If the gamma ray source or the flashlight, right, you move the flashlight to a different location, is slightly shifted left, the projected pattern will shift as well. So this is the projected pattern now that's of interest, and you can see that it's shifted slightly away from the true projection. And yeah, so that's how we see the shift, or the source shifting, and reconstruct the different sources together. I think this is best shown in this image. I took this picture in the London Museum of Science. And this is a coded aperture used for some X-ray imaging in astrophysics. And you can see here that there are 3 different light sources, right? How do I know that there's 3? Because there is 3 different projections of this mask. There is one here, another one on the lower right, and then another one on the lower left. These 3 projections create a coded pattern onto the detector space. So let's say there's a detector behind here. You record that detector, the projection, and you can reconstruct actually where the source is based on this projection. So since the projection is above the mask, you can tell that the light source is actually down here below. While if the shadow is down here and the mask is up here, it could be that the source is all the way up here. And this is the basic idea of how the mask works. The basic math actually is also quite simple. The recorded mask pattern, which is shown right here, this is an experimental image, is basically the convolution of the source distribution and the mask, right? This is, or you can see like almost like a multiplication. This is the source, which is a point source, right? So imagine like a single flashlight or a single point projecting the whatever you're attenuating onto the detector space. This is the projection recording. We can remove the response of the mask by deconvolving out the response of the mask. So this is some decoding matrix that removes the effects of the mask. And then we can reconstruct the source appropriately. You can see here, this is a very good reconstruction. There's another layer into this encoded aperture. It's called time encoding. So not only do we have a spatial coded mask, we move the mask in front. We're going to do that like that. And you can see that the signal corresponds to when there is a hole and when there is no hole in front. So when there's no holes in front, the signal is, the count rate is 0. And when there is a hole there, you can see that you have a spike in count rate. And this is what's called temporal encoding. If you have the source in a different location, you can see that not only is the signal shifted in space, but it's also shifted in time. This is the signal shifted in time. This is how we negotiate the mask movements. Over here is the detector, the CCT detector. And over here, there's a mask that's a tungsten mask. They are, the way we describe the mask is by the number of holes. And in this situation, we use is rank 79 mask. So there are 79 in each repetition of the mask. There are two motors that move it, one in the X and the other one in the Y, and that just helps us encode so we receive the entire coding of the mask. The pixel pitch is 1.4 millimeters, which means the distance between each hole is 1.4 millimeters, and that ties to the resolution of the image and also the resolution of the detector as well. You don't want to have if you imagine you have the aperture so big that you're basically not encoding anything, then it's kind of meaningless. Or if you have so small that you can't resolve the different pixels, that's also meaningless. So this was designed such that it projects a mask appropriate for whatever we're trying to image. This is the basic workings. This is it when it's operation. You can see that the mask translational stage is moving. And over here, you see the projection associated with the different mask locations, right? So your projection into different space. You remember the image I showed you before when I have the different sources for the mask I showed for the X-ray mask. This is basically what's going on. You're moving the projection into different locations. And we record that as the mask is moving. And you can see that when we accumulate all the entire mask, this is the entire signal recorded. And we can convolve that out and reconstruct the signal to create a very high resolution image. There are multiple applications of gamma ray imaging. One of them is in medical imaging. For this as an example of one of the current research of our students, they have here a proton beam, which they're trying to do cancer therapy, radiation therapy actually on the cancer. So they shoot these protons onto some tumor, and the effects of the way the proton interacts with matter is slightly different than that of a gamma ray. What I'm gonna summarize it by the Bragg peak, which means it doesn't deposit any energy at the beginning of its track, while at the end of its track, it deposits most of its energy. So the dose is largest at the end of the track. This is shown right here, right? 0 dose, and then all dose all at once. That is very good for targeted therapy. And the idea is you don't want to hit any healthy tissue, and you want to hit only the sick tissue, which is the tumor. What we do gamma ray imaging, what we use gamma ray imaging for actually, is to verify that the protons are hitting the tumor and you're not having any radial or distal fall off of the actual protons hitting the tumor. And that's important to reduce the dose on the patient and to maximize the radiation targeted on the tumor. And so this is an image of what's going on. They have the proton beam here, and then there's some phantom, and we want to make sure that it's hitting the correct location. So this is a gamma ray image taken with one of the detectors that we have deployed to that location. Another one is in astrophysics, right? We talked about gamma ray detection for astrophysics. This is gamma ray imaging. In the 1990s, there was the Compton Gamma Ray Observatory, which is built by NASA, launched this telescope, which has the Compton telescope, so the Compton telescope. And what they have is a Compton imager on board that tries to image the distribution of the gamma rays coming up front. And you can see that there's a large distribution along the 0th latitude. And that has to do with the Milky Way, I think the plane of the Milky Way, I should say. And also there's a black hole in the middle, so you're basically imaging that. Another one is in homeland security, just like we talked before. So here, or actually also nuclear safety, these are some fuel MOX pins. This is some fuel pins that are mixed oxide. And we can try and image that. And you can see that we can see very well, this is just a few millimeters large. You can see very well the actual pin and the screw that's actually on top of the pin. So there is a screw here that holds the fuel pin in place. That's why you see a dip in intensity in the middle and then a large hotspot at the edges. This is also a plutonium ball that we try to image, and you can see that we can try and construct the distribution of the gamma rays around the source. And that concludes the gamma ray imaging portion of this lecture series. All right,